Hello everyone, I'm excited to present this paper, GPT, Knowledge Graph-Based Prompting for Large Language Models to you. So this work addresses a critical challenge on LLMs, that is hallucination, which is essentially confident sounding but factually incorrect statements generated by the large language models. And this paper, GPT, offers a novel approach to alleviate this problem by grounding LLM's responses in their external knowledge graphs. As many of you know, LLMs like GPT 3.5 and GPT 4 have extraordinary abilities to understand and generate those texts across a lot of various range of the task and backgrounds. However, they can still provide many hallucinations, especially when dealing with those specialized areas or questions that require very specific knowledge. So how can we reduce those hallucinations? One approach is to inject reliable structured knowledge into LLMs, often in the form of the knowledge graphs. These knowledge graphs store domain facts in a structured way, and if LLMs consult them carefully, they can ground their responses into verified data. But most state-of-the-art models like GPT-4 are closed source, so meaning we can only access them via APIs. So the question becomes, how do we reliably feed them relevant facts that are not very hard to convey to the models, that are not very long, not very vague, but are actually very helpful to the models. To address that question, this paper proposes NoGPT, a framework designed to inject domain knowledge or from knowledge graphs into LLMs using a prompt-based approach. And in other words, we only rely on text prompts to feed knowledge to the black box model. No special architecture changes or fine-tuning is needed for this approach. So the framework divides this general challenge into two parts. The first is knowledge extraction, and that is to find which subset of the knowledge graph is the most relevant to the question. And second is the prompt construction. That we will need to automatically generate the best possible textual prompt that conveys the extracted knowledge to the LLMs. So the first part of this approach is knowledge extraction. We will use PRL, which is the policy-based reinforcement learning. This main idea is to navigate through a large knowledge graph. And this knowledge graph will sometimes contain millions of the data, and usually in this paper, or usually in the real world settings, this is in the form of triples, and they will identify which chains of entities or subgraph is relevant to this question. So there are mainly 3 points about this knowledge extraction. First is that it treats the subgraph extraction as a search process. The second is that it defines a reward function that encourages the agent to pick knowledge paths that are very concise and contain the relevant entities and lead them toward the final answer. The third is by iteratively updating this policy network using reinforcement learning. The system learns to extract very high quality reasoning paths from the knowledge graph, and this will avoid avoid noises and redundant details. The next part of this approach is the prompt construction, and the authors leverage this MAB multi-arm bandit to do this. So for this part, we need to turn the knowledge paths into a textual prompt for the LLM to learn the correct knowledge. So for instance, the knowledge being fed to the LLM can be in several ways. The first is the mentioned form, that is the triples, and the second is in a sentence format. The third is in the graph description, that is a more narrative style describing the relationships. So this multi-arm bandit procedure, which is a classical method in the reinforcement learning, will try all those representations out and see how LM will perform. And this approach will finally learn to pick the best format that maximizes the chance of a correct answer. Essentially, it is balancing the extrapolation and exploitation in the reinforcement learning. So these are the technical highlights of NodeGPT. The first is this policy gradient network. So the agent is trained to find the short and relevant paths in the knowledge graph, which this will dramatically reduces the search space. The second is that the context-related and concise, the very concise design of the rewards will ensure the subgraph is strongly relevant to the question, but still remains very short for the LLM to learn. The third is the multi-armed bandit selection. For each question, this method will pick among multiple prompts and feed the extracted knowledge to the LLM. So this combination of those technical highlights will yield a general method that's very efficient and also very effective. That means this method does not overcode the expensive LLM API, and it also selects the knowledge that truly reduces hallucination. So for the experiments, this paper evaluates NodeGPT on 3 benchmark datasets, which are Common Sense QA, Urban Book QA, and Med QA. It also uses 3 baselines, which is zero short version of GPT 3.5, GPT-4, and some fine-tuned smaller language models like BERT and Roberta, and some existing knowledge graph-based methods like QA-GNN. So they will just use the accuracy on the QA task as the evaluation metrics. In fact, on certain tasks, the NodeGPT's performance will even matches or exceeds GPT-4. This is very amazing. So here we can see the results in this right-hand side chart. We can see that LLM with knowledge graph prompting has a very good performance here. And using their specifically designed method, NoGPT, they have reached the best result here. This paper also do some ablation studies on two main perspectives. The first is they uh, delete the process of the PRL, the policy reinforcement, and the policy reinforcement learning. So they find that without PRL based without the PRL based subgraph extraction, the performance will drop very large, and as the system will not give very relevant or those will not give many relevant knowledge to the experimental models. And the second application study is that without the multi-armed bandit approach, this will make the system not able to adapt the prompt style to the question, and this also will reduce the accuracy on the final result. So the conclusion is simple. So both of the PRL and MAB modules are very crucial to this NoGPT approach. Next, the authors give some limitation and future directions for this paper. So the first limitation is that the quality of the knowledge graph. So if the knowledge graph contains errors or lacks some important information, then the LLM's performance is limited. The second is the API cost is really expensive. And the third is the complexity of the implementation remains a challenge. The knowledge extraction policy requires a very well-trained reinforcement learning module, which is not stable in applications. So in the future work, we might incorporate methods of automatically refining knowledge graphs or exploring other ways to minimize the cost and complexity of those prompts. So, as the final conclusion, there are three main takeaways in this paper. The first is this NoGPT method is basically merging the knowledge graphs via and also the prompting methods via LLMs. The second is that they use the reinforcement learning, the PRL for the knowledge extraction, and they also use this multi-arm bandit module for the flexible prompt formatting, which basically chooses the best format from formats like triples or sentences, etc. So thank you all.